So today we will see the implementation of local optimization techniques such as hill climbing for solving AI-based search problem. So let us see a basic hill climbing approach. We see in the hill climbing approach, so this is the visualizer. We have done it using tick enter, and there is a frame button, start button, reset button, the canvas. So the objective function is designed to create a surface with multiple peaks. Then the surface is initialized, and then the hill climbing function starts. So we define some variables, current x and current y, and current z. Describe the objective function using the current x and current y. Step size is 0.1. So we plot an initial position, and then we generate the neighbors. In the hill climbing, we explore the neighbors. So by the step size, so current x plus step size, then current x minus step size, current y plus step size, current y minus step size. So these four are the neighbors, and then we find the best neighbor or with having best value, and if it is that better than the best value, then we consider that as the next point to move ahead. So if no better neighbor is found, then we have reached a local maximum. So in this way we can find out, and we can start the hill climbing randomly, and we can also reset. So let us see. So we now see a surface looks like with some crests, troughs, maximum. So if we start the hill climbing, we can see it has reached the local maximum. Although it is not able to go to the global maximum, it has reached the local maximum at minus 1.32, minus 4.96, 1.1. So if we do a reset and again start the hill climbing, you can see here so it has found a local maximum at 3.43, 1.39, 2.7. So current x, y and z, these three positions are described here. So if we want to enhance this with the simulated annealing, so simulated annealing will involve, again if you see, this is the enhanced hill climbing visualizer with simulated annealing. So if we go to the get visualization update interval based on speed setting, objective function, we have defined a more complex surface with multiple peaks, and we initialize the surface, update visualization. The simulated annealing, we have a temperature. So the temperature initially is set to 1, and it is slowly decreased by the cooling rate. So this temperature helps us to explore more solutions in the beginning and then converges to more optimum solutions. So this is how it works while temperature greater than mean temperature. So we find generate the random neighbor, and then this is the accept or reject new solution. If we see a delta E greater than 0, first of all it finds some worse solutions, and then it gets better as we reduce the temperature. So this is how the simulated annealing works, and we have coupled this also with the basic hill climbing algorithm. So you can see, so now let us run this. and test it. So let us run this. So now we can see this basic hill climbing, and we start the optimization for the basic hill climbing. So it finds a local maximum, and but if with a simulated annealing, so it will find us the global maximum. Simulated annealing will always help us to find the global maximum, but basic hill climbing can find local maximum. So that is how the simulated annealing works to find the global maximum. So now let us also see how this hill climbing algorithm can help to solve a maze problem. So therefore we define a maze, and we define a start and the goal node. Then we generate the maze, and we set up the directions, and we draw the maze. Then we use the Manhattan distance, and we find the neighbors. So then the hill climbing is started. So maximum number of restarts is given as 50. So now we find the neighbors. There is a filter of unvisited neighbors. If not unvisited, so backtrack if stuck, choose the neighbor that minimizes distance to goal. So this is how we use the Manhattan distance here. Then we visualize the current position, and the next position is assigned to the current, and we append that to the path, and the current is appended to the visited nodes. So this is how then we find the path. So our maze solving starts with the hill climbing solve, and if success, then path is found, else could not find path. So let us see. Now we can see this maze. So we will solve with hill climbing. So a path is found, and we will generate a new maze, suppose solve with hill climbing. So it generates the neighbors, and then it searches for the path. So this is how the path is found in the use of hill climbing for maze solving problem. So thank you all.